Hi, everyone. We're just going to start part 2 of the Strategic Energy Seed Grants. So the first one we have is industrial decarbonization, the first area, and then produce water treatment and reuse, and battery production and critical minerals. So first, we'll start with mitigating voltage sag disturbances for electrified industrial process loads. And that will be presented by Damian Zechovich and Hien Seong Moon.
Hi, everyone. Thank you for joining us today. My name is Damian Zechovich, and I'm joined together with my colleague Hien Seong Moon. I'd like to start off by thanking the Energy Institute and our collaborators from Shell, also Dr. Lei Jiang, our PI, Dr. Surya Santoso, and our co-PI, Dr. Brian Johnson, for allowing us to work on this project. And I'll start off by mentioning that voltage sags and under voltage conditions can severely impact industrial loads. These power quality issues can cause malfunctions, which can cause misoperation, inefficiencies, and economic losses. To illustrate a voltage sag, we show the figure where we can see 3 phase voltages represented in different colors at nominal levels. Once a voltage sag occurs, these values go down to a minimum value until the fault is cleared and all the values are restored at nominal levels. To address this, we represented an industrial grid model where we incorporated compensating devices such as STATCOMs or static synchronous compensators and DVRs or dynamic voltage restorers in order to enhance the voltage stability. We evaluated their performance to assess their effectiveness, and we optimized their placement in the system. So our objective is to mitigate the voltage sags and the under voltage conditions at the load terminals. Our approach is first introducing the STATCOM to the system to tackle the under voltage conditions and improve the overall voltage in the system. We used the DVR to inject all the missing voltages during a sag event until the fault is cleared. And we optimized their placement based on the fault magnitude, its duration, and how it affects the equipment. So our accomplished work so far is modeling these devices. We accomplished modeling the DVR in fall 2024, and we also modeled the STATCOM. Next, we developed the industrial grid model. So we did the utility source, the feeders, the transformers, and the inductive motor loads. And finally, we optimize the placement of the DVR and the STATCOM to minimize the effect of these disturbances. Next, I'll allow my Hien Seong to continue.
Hi, my name is Hien Seong, and let me continue with the object of STATCOM. STATCOM, the purpose of STATCOM is to mitigate the voltage and enhance the voltage stability. And the bottom left, there is a STATCOM structure. First one is a DC link, which can install the energy. And next part is the inverter module, which can convert the DC voltage to the AC voltage. And third one is the AC harmonic filter, which can eliminate the unwanted harmonics. And next one is a step-up transformer, which can make the appropriate voltage for the grid. The last one is the most important one, control block. It monitors the voltage and the current and makes some appropriate apparent power to the grid. And it injects reactive power to the grid, and it makes the voltage. On top right, there is a voltage improvement with the Statecom operation. We can see that it is steadily increased and stabilized after the operation of Statecom. And when we consider how we placement of the DBR and Statecom, there is two main options. First one is near the utility, and second one is near the load. Near the utility, you can install the one devices, and it can compensate the cost efficiently. However, it cannot make some respond to the regional voltage problem. However, if we install the near the load, it can compensate directly to the load. However, it may need the spatial consent and increase the control complexity. Now let's move on to the optimal placement of the DBR and Statecom. Here's our grid, and there is a tentative placement for the Statecom and DBR. There is a 4 strategic space for Statecom, and there is the two DBR for the load. The location for DBR is laid to the next part. Going to the bottom of the left, there is the 4 frequency location pattern. And according to the APRI, most of fault occurs in the industrial grid. So to protect the industrial load, DBR should be installed near the industrial load. Now let's move on to the table on the right. There is our result for simulation. For example, if we install the bus 6 and bus 7 and Statecom, we only need the 76.85 megabar, and the voltage at the bus at 6 and 7 is increased by 10% and 40% each. And finally, we also represent a graph for the DBR. These graphs tell how DBR and Statecom cooperate to mitigate the voltage. So in the normal operation, Statecom boosts up each voltage, and with the fault duration, DBR restores the sagged voltage. And after all, DBR and Statecom can complementarily load with each other. So in conclusion, DBR and Statecom make a voltage enhanced with the industrial grid. And with the optimal placement, we can achieve the cost efficiency and the power quality enhancement. Thank you.
Any questions? Anyone? No? Okay. All right. Next, we have the evaluate. Wait. Next, we have from solar panels to sustainable concrete, development of solar waste glass Patsolan.
Hello everyone, I am Anirudh. I am a postdoc at the Department of Civil and Environmental Engineering here at UT Austin. So today I will talk about how we can reuse waste solar panel glass as a building material. So solar panel has been a big growth story. As we are going away from fossil fuel derived electricity generation, we are investing more into making solar energy, and after 30 to 40 years, we expect these solar panels to be decommissioned. And as they get decommissioned, generally what happens is there are companies that tries to recycle these solar panels. Specifically, the aluminum frame is very easy to recycle. Companies are interested in recycling the solar cells as well because they have precious metals in it. But the glass component is hard to recycle because when people separate the solar modules, you have impurities that goes into the solar glass, so you cannot make solar glass again from the waste solar glass. So that's why it's very hard to do closed loop recycling of solar glass panels. And that's why we are looking at open loop recycling. It is very important to state that solar panel has 70% of the whole material by mass is solar glass. So if we are looking for achieving a circular economy, it's very important that we actually do something with the solar glass and not just landfill it. So what is cement or concrete, right? So in concrete, the major binding material is cement that reacts with water to form something called calcium silicate hydrate that binds the aggregates together. This is what gives us the strength. Here we will try to use solar panel waste glass as a pozzolanic material. Now, what is a pozzolanic material? So when cement and water reacts, calcium hydroxide and calcium silicate hydrates are the major hydrated products. Now, the calcium hydroxide can react with amorphous silicates that are in the solar glass to form calcium silicate hydrate again. So this kind of helps us to reduce the amount of cement in the concrete by replacing the cement with solar glass panel. And also I would like to point out that currently there is a supply deficiency for pozzolanic materials. Specifically, the most common pozzolan is the coal fly ash, and as coal power plants are closing, we have a supply issues in some parts of the United States. So it kind of fits together that as we are going away from coal power plant, we have this new material that can replace part of the supply of pozzolans. So if we talk about motivations, there is already some industrial standards available for using glass as a pozzolanic material. So we can use it to verify that our material actually conforms to industry standard. And also, as I mentioned before, demand for pozzolans is very high right now. And the way we are going to do it is we are using waste glass from a company, and then we grind it very fine in the lab so that it can react with the cement and water, and then use it as a cement replacement. Now, if we look at the elemental composition of the solar glass, right? So we have two solar glass 1 and solar glass 2. We are comparing their results with a reference glass, which meets the ASTM standard. And we can see that mostly the silicon content is very high throughout, which is the amorphous silicon that we are very interested in. The magnesium contents are a little bit higher in solar glass 1 and solar glass 2. Generally, people add more magnesium in solar glass to increase its toughness. The iron content is much lower. This is because in solar glass manufacturing, people make sure that the raw materials does not have a lot of iron to improve the transparency of the solar glass. In terms of mineral composition, we found that both the reference glass and solar glass 1 and 2 are fully amorphous. So this is very nice because we actually want amorphous silicate to react with the calcium hydroxide. We measured the particle size of these solar glasses and the reference glass and found that our solar glass 2 was a lot more coarser than the solar glass 1 and reference glass. So this grinding was done in the lab. So there is some difference there as well. So just moving forward, remember that solar glass 2 is the coarser one. In terms of performance of solar glass as pozzolanic material, at first we started with something called measuring pozzolanicity. So this is the fundamental reaction that is valid for all pozzolanic materials, where calcium hydroxide reacts with amorphous silicate to form calcium silicate hydrate. And we would like to quantify the amount of calcium silicate hydrate that forms, and we have used two different methods for it. First, we used the amount of water bound in the calcium silicate hydrate as a measurement of how much calcium silicate hydrate is being formed. And also we used a calorimeter measurement where we evaluate how much heat is being evolved over time to see how much calcium silicate hydrate is forming. We found that the solar glass 1 and the reference glass behaves quite similarly, both in bound water content and in heat release. But solar glass 2 was much worse in pozzolanic reactivity, again, because it is much more coarser. We also tried to put it in cement and water and try to see how it actually reacts with cement with cement, water, and solar glass together. And we found that, again, the reference and solar glass 1, which are the finer ones, they react kind of very similarly, and the solar glass 2 was worse because it was much more coarser. Mechanical strength is the 7-day compressive strength. It was kind of similar throughout, so we don't really see a major difference there. In terms of main findings, I would like to emphasize the following. Solar glass basically behaves very similar to the other glass pozzolans currently being used in the industry today. So if we want to scale it up, the way to do it would be to collaborate with some companies that are already recycling solar panel, and they are sending the waste glass to landfill, but we'd like to put like a ball mill to grind it fine and try to sell it as a pozzolanic material. And it is that's why I feel like it is relatively easy to implement in grand scheme of things, and it is very cheap. Grinding solar glass panel from 2 millimeter to, let's say, 5 micron that we need for it to work as a pozzolanic material is quite cheap. It's cost about $10 per ton, very rough calculation estimations. So I would like to thank UT Energy Institute and Circular Solar USA for providing the materials. Thank you.
Gary Rochelle at the Chemical Engineering Department. Would this compete with just normal recycled glass doing the same thing? How is it better than that?
It can compete with the recycled glass. So the main question here is people these days, so what happens in recycled glass, people already have the supply side built up. So from the waste recyclers, they get the glass bottles and then they grind it and sell it to the concrete people. For solar glass, this supply chain has not yet been built up. So that's why we are trying to say that, the same way the recycled glass is being used, the solar waste glass can also be used.
Good morning. Thank you for the presentation. You mentioned calculation of the cost of 2 millimeter glass. Have you looked at other millimeter glasses and also different heat treatments and also different chemical compositions for absorption? Or have you just looked at like a standard and then you're going to expand on that later? And also, have you thought about using the glass for pavement as well as concrete?
Very interesting question. So for now, we are just using 2 waste glasses. And so we are collaborating with a company that already does some of the separation of the solar panels. So from them, we get the glass cullets, and they provide it at the size of roughly 2 millimeter. And then right now in the lab, we are grinding it down to below 45 micron. And in terms of using it for pavement, of course, you can use it as a cement replacement for pavement applications. If you are from pavement community, I'd be happy to chat with you about it.
Any other questions? I'm just curious, actually, how much glass from solar panels, how many solar panels are already out of commission overall that have the potential to be used for this type of...
So this is more like a futuristic outlook. So if you look at the amount of waste module that is being generated, right now we are in we only have maybe less than 1 million ton or 2 million tons that are available, but per year. And as the solar panels are being made and being used, after some time, let's say 20 years or so, we should have a very high supply picking up.
Great presentation. I love process engineering at heart. I love simple, convenient processes. Simple is not easy to achieve. This may not be a great startup, but this is a huge problem that I actually can see we need to deal with. So my first thought was, your proportion of kinetics versus particle size. That's just typical catalysis or grinding.
Yep.
People will figure this out, but this is a huge problem. So keep doing this work. It's very needed.
Thank you.
And our next talk will be on the evaluation of a novel integrated ceramic membrane, hollow fiber membrane contractor process for the produced water reuse, presented by Julia McGuire.
Hi, my name is Julie McGuire. Thank you all for coming today, and thank you to the Energy Institute for having me. I'm a graduate student working with Dr. Lynn Katz and Dr. Frank Seibert on this project for the evaluation of a novel integrated ceramic membrane and hollow fiber membrane contactor process for produced water reuse. Produced water is a major byproduct of the oil and gas industries. It has a complex composition, including dispersed and emulsified oils, suspended solids, salts, heavy metals, production chemicals, among others. Large volumes of produced water are generated by the oil and gas industry, and currently the majority of this water is disposed of via injection into the subsurface. This project is looking to investigate a treatment process featuring 2 different membrane technologies to enable the reuse of produced water. In our process, our first step includes oil removal via a hydrophobic hollow fiber membrane that utilizes selective oil permeation to permeate oil through the membrane, removing oil from the water and recovering a very high quality pure oil stream that can be recovered by oil and gas operators. This technology and this step in the process has been studied by previous works with the Energy Institute to very successful results. You can see in that photo there in the top left a comparison of our raw feed to the hollow fiber membrane and the treated effluent coming from that from the membrane. Again, we achieve very pure oil in the permeate stream and very oil-free water in the concentrate stream. The integrated process then features a ceramic membrane to follow the hollow fiber membrane to remove small suspended solids that are rejected by the hollow fiber membrane to achieve an overall very pure, clean water stream containing less than 5 parts per million oil and grease and 5 parts per million suspended solids. So my work specifically focused on evaluating and investigating the performance of the ceramic membrane following the hollow fiber membrane and how that integrates into the process. Our experimental process included bench and pilot scale testing of the ceramic membrane. We implemented an aluminum oxide cross-flow membrane with an average pore size of 5 to 8 microns at both the bench and pilot scales. The pilot scale membrane allowed for a 10-time increase in membrane area and 10-time increase in process flows. We constructed our experimental systems at the Separations Research Program at the Pickle Research Campus. The process begins in the mixing tank where our model TSS solutions are then fed to the ceramic membrane, and the permeate and retentate streams are recovered and recycled back to the mixing tank to allow for continuous operation and to maintain consistent TSS concentrations throughout our testing. We included flow meters and pressure transmitters into all of the streams so that the process performance could be monitored and the data could be collected and stored using Delta V software. And we also included sampling locations to sample and test TSS concentrations during our experiments. We also implemented a backwashing mechanism from the permeate side of the process. We backwashed with treated permeate and also pressurized nitrogen gas periodically to help remove any TSS particles that may build up in the membrane pores over time or on the surface to increase average flux throughout a run. The model TSS solutions consisted of distilled water or actual pre-treated Eagle-Ford produced water from the Eagle-Ford Basin in Texas, and TSS particles of sandstone in the range of 20 micron to 100 micron, or aluminum oxide particles in the range of about 1 to 8 micron to test the efficiency on very fine particles, especially because our membranes do have a 5 to 8 micron pore size. We wanted to test the performance on particles that were close in size or smaller to the pores of the membrane to see if we could effectively remove those as well. Here are some selected results from some of our testing. Here on the left side, you see the results from our 1 micron average size particle testing or particle solution we can see that the ceramic membrane was able to obtain very consistent and very effective TSS removals across all conditions, achieving over 95% removal for all of our tests. We see that feed, TSS concentration, and transmembrane pressure have very little effect on the TSS removal of the ceramic membrane. And for permeate flux, we see that with feed TSS concentration increasing, we do see a decrease in permeate flux. Similarly, with increasing transmembrane pressure, we see decreasing permeate flux. This is due to more rapid fouling of the membrane. We did implement 5-minute backwashing cycles to the process, and that we saw effective results at recovering permeate flux and improving average flux over our runs, but we still see those effects at certain conditions. On the right here, I'm showing some preliminary results of the effect of solids in the presence of the feed solution to the hollow fiber membrane, as this was conditions that weren't tested in our previous work. Here we introduced 5-micron aluminum oxide sized particles to the feed to the hollow fiber membrane in the selective oil permeation process in concentrations up to 100 ppm. And we see that the presence of these small solids had very little effect on oil recovery, and we were still able to maintain effective and consistent oil recovery from the hollow fiber membrane. So in summary, the effluent from the integrated process consistently achieves less than 5 ppm TSS concentrations and oil and grease concentrations. And we see that the larger pore size does achieve effective TSS removal even at smaller particle sizes and improved flux as compared to coated ceramic membranes or membranes with smaller pore sizes. And our future work with the Energy Institute looks to test and compare the performance of a silicon carbide ceramic membrane, as some literature suggests that you can obtain higher flux with these membranes as well. And with that, thank you all for your time, and thank you again to the Energy Institute.
Questions?
It's a great presentation. Just kind of looking ahead, I know this is obviously early in the research process, but to commercialization, what kind of volume are you projecting, just in terms of being able to process, higher volumes?
That's a great question. We have done some work with some of our partners on this project, trying to incorporate an economic analysis and start to answer those questions. Yeah, we've just started work on the pilot scale, so I think looking more at the results from that, we can perform a better scale-up analysis and start to answer those questions. I think right now it is a little bit early to say, but we are seeing with the larger pore size that we're able to treat water more efficiently, or get higher volume generations with that. So it is a major goal of ours to address those concerns.
What are y'all looking at as kind of have y'all done testing as to what the life cycle would be on the materials?
So ceramic membranes are very durable. They can withstand a lot of variability in your feed solution and the conditions of your process. The hollow fiber membrane is a polymeric membrane, so those traditionally are seen as maybe less durable. However, we've been operating our hollow fiber membrane with this process for a very extended period, and we've seen that over time, actually, the performance is only improving due to the selective oil permeation process and oil wetting of the membrane surface. So, in fact, we're seeing that the process is very durable, and we're expecting a very long lifespan for the process.
Here you go.
Make you exercise. I was curious if flow rate affected the efficiency removal. Like, did you test faster versus slower flow rates?
Yes, that was another parameter we tested. I just selected some of our results for time's sake, but we have seen that there's, give and take with the flow rate as well. usually too low of a flow rate, you lose the flux. It's all about kind of finding that sweet spot, and that's been another parameter we've looked at as well.
Okay. Our next presentation will be on the technical and oh, go. Yes, go ahead. All right. I think that the question on scale is also a good segue into this technical and techno-economic analysis of produced water treatment for green and blue hydrogen production in Texas. And this is going to be presented by Shantanu Katakam.
So, good morning to everyone. I'm Shantanu Katakam. I'm a PhD student working under Dr. Vaibhav Bahadur, who's an associate professor in the Department of Mechanical Engineering. And today I'm going to be sharing about my research on technical and techno-economic analysis of produced water treatment for green and blue hydrogen production in Texas. So first, I would like to give you some background about the clean hydrogen production's water problem, which is basically that clean hydrogen production generally requires significant amounts of high-quality input water. Quantifiably, it's like for 1 kg of hydrogen that you want to produce using electrolysis or fossil fuel reforming with carbon capture, you need at least 20 to 30 kgs of fresh water. Now, this fresh water can be of two types. One is the processed water, which is required for the actual process, and it needs to be ultra pure, which means the total dissolved solid should be less than 2.5 ppm. And there is another type of water that is also required for this process, which is the cooling water. That can be of industrial quality grade, that is of TDS less than 2000 ppm, and this water is used for thermal management. So the figure that's shown here gives a detailed breakdown of the freshwater requirements for 1 kg of clean hydrogen production. These numbers have been taken from different agencies, including IRENA, US Department of Energy, etc. So given that we have a global water scarcity already, the implications of sourcing this fresh water for clean hydrogen would be debatable in future. So we actually identified that with adequate pretreatment, on-site produced water desalination can actually meet the freshwater requirements for clean hydrogen production. So, but in general, on-site produced water desalination itself is a challenging task because of the hypersaline nature of the feed and also the spatio-temporally varying chemical composition and flow rates of the produced water. So to put things in perspective, produced water from Permian Basin is produced at about 20+ million barrels per day with an average TDS of 94,000 ppm, which is already hypersaline, and most of it is NaCl. So here we look at 3 different techniques which are conventionally, 2 of them are conventionally used for produced water treatment, and one of them is an unconventional technique that we are pursuing. So the conventional techniques are reverse osmosis and mechanical vapor compression. So as you can see, RO is quite restricted in its salinity range, and hence it's only suitable to treat 22% of the produced water from the Permian Basin. That's just because it's having a burst pressure limitation. Basically, the membranes cannot withstand the pressure that is needed to purify your produced water, that is hypersaline. But given that it's a membrane-based technique, it's quite energy efficient and economical. Now, when it comes to the typical produced water treatment technique, which is a mechanical vapor compression, that is a thermal-based technique, it is suitable for about more than 75% of produced water that is being obtained from Permian because it's quite insensitive and you're just boiling off water to purify it. But it's quite energy and capital intensive, which is one of the primary challenges for adopting this technique for produced water desalination in general, and also for the clean hydrogen production application that we're considering here. Now, we are pursuing a new technique called osmotically assisted reverse osmosis, which kind of has a best of both grounds, I should say, because it's suitable for 35%, and the TDS range that you're seeing is quite hypersaline, so it kind of extends the salinity range of a conventional reverse osmosis. But since it's a membrane-based technique, the extensive pre-treatment and the suitability, the extensive pre-treatment and the commercialization aspects are still an issue. But given that it's both energy efficient and also suitable for hypersaline produced water, it kind of forms a middle ground between the both conventional techniques that's being used today. So next I'll move on to some of the important results for that we have done by modeling both the unconventional osmotically assisted reverse osmosis and the conventional mechanical vapor compression for the application considered. as you can see here, for every 1 barrel of produced water that is being purified, we get about half a barrel of fresh water that can either be used for process water requirements or cooling water requirements for clean hydrogen production. So the first two that you can see on the top are the coupled osmotically assisted reverse osmosis and RO, which is the technique that we are pursuing. And the last one that you're seeing is mechanical vapor compression. So you can see that for every 1 barrel, you get half barrel that is suitable for process or cooling water. That's the hydrogen water problem being solved. And we are also simultaneously solving another problem, which is that the concentrate that you're getting from each of these desalination techniques is quite saturated. I mean, it's close to more than 177,000 ppm, and therefore it's also suitable for environmentally friendly zero liquid discharge. So in that way, we are kind of also solving the produced water management problem in general, and also the clean hydrogen water requirements problem. So to put things in perspective, for every 1,000 liters of produced water in the Permian that we treat, we get about 15 to 24 kgs of clean hydrogen if the fresh water is split between process and cooling water. Whereas we get about 175 to 312 kgs of clean hydrogen for reforming and 46 kgs for electrolysis if the fresh water that we obtain is just used for the actual process itself. So when we go ahead with comparing the cost and energy of each technique, you can see that the technique that we are pursuing, which is OARO, is slightly costly. It costs about 2.5 to 2.6 cents for every gallon that you purify, whereas the conventional mechanical vapor compression just costs about 2.48 cents. But when you see with respect to the energy consumption, because the technique that we are pursuing is a membrane-based technique, it's almost more than half of the energy is reduced, where it just costs about 102 kilojoules for every gallon of produced water being purified. Whereas a mechanical vapor compression, because it involves phase change, it requires 281 kilojoules per gallon. So in this way, we are kind of analyzing both the unconventional and the conventional produced water treatment technologies, both techno-economically and thermodynamically, so that we can solve the problem of produced water management and also the water problem for clean hydrogen production simultaneously. Yeah, thank you.
Thank you. Any questions? Okay. All right, well, next we are going to have the discovery of modified phosphate solid electrolytes for all solid-state sodium batteries. And it will be presented by Callum Campbell and David Mitlin.
All right. First, thank everyone for being here and letting me talk about my research. Chance to get out of the lab is always welcome. So I realize I probably should have started with more background on this first slide. We're trying to make batteries, and we want to make lots of them very quickly, cheaply, and sustainably within the United States supply chain, or at least a stable one. So we're looking at new technologies to make that feasible, make it economical. One of those is solid-state battery technology, using sodium rather than lithium. It comes with its own challenges, but the benefits are huge. And again, I didn't include all the economics on here because I spend all day in the lab. But the abundance of sodium within the Earth's crust is hundreds of times that of lithium. So we're looking at a much more sustainable, equitably distributed across political boundaries. And we're trying to make sodium a viable option. One of the hard parts is getting the kind of energy density you would need for something like an electric vehicle. You want as much charge per unit volume or mass that you can possibly cram into a battery because you want to get your money's worth when you buy one of these cells. To do that, we think you need solid-state technology. So we want to remove the electrolytes, basically two reasons. One, to enable metal batteries rather than based on carbon anode materials. Two, we hope to reduce the flammability of these batteries on the whole scale. So the organic liquid electrolytes used in the lithium-ion batteries in your phone or in a traditional EV are flammable, and we're trying to mitigate that risk. So what I have been working on, and in this project with all of our great collaborators here, is to modify the synthesis process of a traditional state electrolyte system. So this is based on Nasicon, which is a sodium zirconium silicon phosphate discovered by John Goodenough, of course, like everything else. So what we did here really ended up working better than I expected, really better than any of us expected. We decided to take the traditional processing route, which would be to mix your powders, grind them up, fire them, grind them up again, and press them into pellets to get a nice ceramic compact. And this ceramic should be able to conduct sodium ions and act as the electrolyte in our batteries. We replaced two of the precursors with a more reactive version. So rather than using zirconia, we use zirconium carbide, and the same for the silica to silicon carbide. Our initial thought process and the results show that the carbides tend to combust during the firing process, and we get a modified microstructure. In most of the literature, most of the work being done on these ceramic materials, you're trying to study your material, but the actual result is a composite. So if you look here, you see a lot of features going on. We see bright particles. We see darker areas within the sample. Those are not what we want to be seeing as researchers. I'm trying to make this sodium zirconium silicon phosphate. It's a particular crystal structure, and it should be able to conduct sodium ions. But these other things aren't necessarily going to do that, and our goal is to try and figure out how to create this modified structure and use the varied composition of the final product to tune the safety and performance of these batteries. So I'm going to show you some results in a second that, surprise, surprise, this material does work a little bit better in some really important ways. So our approach is to modify the reaction pathway, create a modified microstructure, and we get some better performance. So our performance testing is to assemble these into what we'll call a symmetric cell. So it's not exactly a battery. We're taking metal anodes on both sides, and we are sort of stress testing the electrolyte. We're trying to measure its conductivity, and you can see here compared to a baseline sample, the conductivities are pretty comparable, but we have a slightly purer sample. We get less of the side products in this reaction, so we've kind of improved the efficiency with a pretty small change to the processing condition. But the real issue is not how conductive these electrolytes are. The real issue is how resistant they are to catastrophic failure. And the catastrophic failure route here is going to be the growth of metal filaments, like you see here, through the solid electrolyte, connecting the anode to the cathode within the battery. And that's going to cause a short circuit. That's going to ruin your capacity. That's going to be a complete failure. So our basic approach is to stress test our cells by progressively increasing the current until we get one of those short circuits to occur. So what we want to do is we want the current to go as high as is conceivable before we get a short circuit so that we know that these batteries are actually safe. What you're looking at here in red is our baseline sample made from essentially an average recipe you would find looking through the history on this material. By just switching out our zirconium oxide with zirconium carbide, we're able to achieve a 6-fold increase in what we call this critical current, the current rate that we can cycle before the cell fails in this way. So this 6-fold increase was a bit of a surprise to us considering the activities are quite comparable. So we're trying to dig further into how this modified microstructure with essentially the same chemistry as the traditional material is able to resist the growth of these metal filaments. So in a great collaboration at the user facility out at SINT Sandia, we went and we did cryogenic microscopy using a FIB-SEM to take a few of these images. And we're basically, at this stage, trying to understand the fracture mechanics, which is really the issue with these ceramic materials. We're trying to understand how do these metal filaments push their way through, open the cracks, and why does one microstructure, I'll jump back, why does one microstructure like this behave in a different manner than the traditional microstructure you might end up with? So we've got some people working on simulations of that. We've got 3 different phases. If anyone here studied physics, you'll know that 3 bodies interacting is always a pain. So there's not a lot of easy, straightforward explanations. But we're kind of taking our quantified microstructure, trying to figure out how many of these secondary particles there are, what is their size, what is their distribution. And hopefully we can actually answer this question of why our material works so much better than we set out. And then I have one more slide, just to show this image one more time, mostly because I was sitting in the office looking at it one day, and one of the new postdocs that had joined the lab after I got in and was looking at these images, he looked at this and said, "Oh my God, how have you not published that yet?" So I figured I should show it to you all. This is one of those metal filaments growing through the material. I won't tell you how many hours it took to get this image. And of course, I'll thank the Energy Institute, the SEED program. I'll thank the Texas Materials Institute. We used a lot of their user facilities, and Sandia and Los Alamos for access to the equipment we needed. And that's if anyone has questions.
Alex Roy, Group 1. I'm also a fan of Beyond Lithium Materials. Are you a grad student or postdoc?
I'm a grad student. Yellow. There we go. I'm a grad student. This is my second year.
Do you want to join a startup after?
Not a bad idea.
So interestingly, it's funny how things come around. Professor Goodenough invented this material in the 70s.
Mm-hmm.
And now we're looking at Beyond Lithium, and it's coming back as a viable alternative for a solid state. So it's just, there's been several innovations that have come from his lab that is now, you know, obvious now, but he was focused on it first. So anyway, let's talk after.
Will do.
So are you saying that this metal growth here is a failure for the material, or do you think that it's a protective?
It is a failure, yes. Okay. We are pushing these things until they completely fail, and this is a post-mortem analysis, I would say. Because as soon as that metal filament connects the anode to the cathode, electrons will flow through the cell instead of ions, which is the goal, and then you get no energy out the other side.
Right. Okay, thank you.
Thank you. And also, a lot of these projects do have posters in case anyone came in late over there in the other room next to us. So, you know, you are welcome to also speak with the researchers potentially there and take a look at more of their work. The next that we have is scalable tissue-inspired lithium extraction, electromechanical membranes, and it's presented by Hare Krishna Behera.
Hello everyone, my name is Hare Krishna Behera. So I'm working with Professor Manish Kumar at Civil Architecture and Environmental Engineering. So today I'm going to discuss about a biomimetic membrane that can be used to separate lithiums. So as all of you know that how much lithium is important for our energy and as well as to transition to clean energy. For example, the lithium ion is widely used in lithium-ion batteries, and that can be used to store energy from renewable energy storage. And also, the stored energy could be utilized to power electric vehicles or portable electronics. So since the demand of these electronics are growing, so the demand for the lithium is growing up, and it's projected to grow up in the near future. And this is the graph of critical minerals importance to energy versus its supply chain risk. And although lithium is having a moderate supply chain risk, but it takes the position as highest in importance to energy. That's why, so every country should secure their domestic supply to meet their energy demands. So, but the current technology to extract lithium from brines or ores are inefficient, have low selectivity, or use excess chemicals that is damaging to environment. So the major challenges we are facing because of the low size difference between lithium and the other commonly found ions present with the lithium in the brines. So for example, the size difference between lithium and other ions falls below 0.5 angstroms, and that's the main reason we don't have a proper membrane that can separate this. So since size cannot be a major discriminating factor, so our approach to use affinity to a specific ions could be used as a discriminating factor. So we actually inspired by the biological systems such as membrane proteins and how they selectively transport one ion over the other ions. For example, this is a potassium channel, and this protein allows its functional groups to come close and make a selective filter, and that selectively filter potassium over the sodium ion. But we cannot use this protein outside of the body because these are unstable. So our approach is to use artificial ion channels. So we use artificial ion channels because these are small organic molecules, and these are stable and can be scalable, and the functional groups of this channel can be easily modified. So the main idea to use this type of molecule that if we incorporate into a membrane, so the the functional group present at the channel entrance can have a favorable or unfavorable interaction with various ions and can selectively transport one ion and can reject others. And if this channel is selective to lithium, and then it can selectively transport lithium, and we can use this approach to separate the lithium ions. To support this hypothesis, we first synthesize this channel in our lab, and then want to test its selectivity over the membrane. For this, we use a model membrane, and it's a lipid bilayer. And in this setup, what we do is to make a membrane and incorporate these channels in the membrane. And this setup, this membrane separates two electrolyte chambers, and then we apply two electrodes in both sides of the membrane and apply potential difference. If this channel transport ions, then ion will carry the current and go to the other side, and that can be detected. So this is the result, and here we see that, and these channels, this is the current output at different applied potentials, and this IV curve shows that our channel prefers to transport lithium ion, and the current output from other ions are same as their background current. And from this we calculate the conductance, and from the conductance we calculate the selectivity, and we found that our channels prefers to transport lithium ion at a rate 100 times higher than sodium and potassium, and more than 200 times than calcium, and around 500 times than magnesium. So there is a challenge here. The membrane is only 200 micrometers, so it cannot be scalable. So we want to develop a scalable membrane. That's why we use this biomimetic approach to develop a scalable membrane. And for this, we use a droplet interface bilayer chemistry. So for this technique, what we do, we take a monolayer of lipid in water droplet and add to the oil. If you add to the oil, the polar side of the lipid will point towards the water, and the non-polar side will point towards the oil. And then when you make it close together, there is a lipid bilayer here. So, and if channel is present on this bilayer, and then ion can transport from one side to the other side through this channel. So we use this concept and take millions of these droplets of monolayer of the lipids, and then centrifuge it, and then make it jam together. So when we jam together, these monolayers of lipids, they're interconnected three-dimensionally and form a interconnected membrane. And in the microscope, we can see like how the droplets are interconnected with each other. And this looks like a gel, and this gel can be put in or installed in a measurement cell, and here, and this gel can be supported by two hydrogel layer, and we can put two electrolyte chamber both the sides and apply two electrodes, and similar to the previous experiment, we can apply potential difference here and get the current output. So while we test our original channel, we can see that during the membrane fabrication process, this precipitates. That means our original channel, although we can see the activity in the small membrane, so for this it is not compatible. So, and we found from the literature that that some of the amino acid side chains can help to go into these lipid membranes. That's why we make few different variants of this artificial channel by attaching amino acids with tryptophan and phenylalanine, and we found that this variant is more membrane compatible and doesn't precipitate. And then we incorporate into the scalable membrane, and here is the data conductance of each ion, and from this we found the selectivity that lithium is transporting lithium at a rate 160 times higher than sodium, 246 times higher than potassium, and more than 300 times than the magnesium. And we are up to now, up to this, and I would like to thank all of my team members, UT Austin for facility, and Energy Institute for the funding. And thank you. I would be happy to take any questions.
Any questions for Hare Krishna?
Thank you for the talk. Thank you for the talk. Do you find that the selectivity is mostly based on the size of the ions? And could you speak to trying to separate other ions like sodium or potassium?
Basically, when we actually collaborate with Professor Venkat Ganesan to find out the selectivity, like how it filter lithium and why not others. So if we go back to this channel, so the PO-PH2 group, the diphenyl phosphine group, this strongly interact with the sodium and potassium ions. And because of the strong interaction, this those ions get stuck there. And the lithium is having very moderate interaction here and the oxygens, and it just hop through this channel. And for the magnesium, that doesn't get any interaction from the functional groups, and the hydrated size is very big to pass through. So to your question, actually it is a combination of the affinity and the size.
Any other questions at all? Okay, well now we are going to start lunch. We also have an entrepreneurship mixer that will be taking place over here. So these are all of mainly our CEOs and founders and individuals that have been through, entrepreneurship. Like, go talk to them, especially if you're considering a startup, or if you're just curious, or if you're looking to go into that field. As well, we also do have voting for the poster competitions. So if any of you want to vote on the Audience Choice Awards, there is money at stake. And thank you so much to all of our researchers and our professors for working on these projects. And thank you.